What we are going to do now is to try to understand from a quantitative point of view how can we find what expression there is that tell us the concentration of reactants, say for any kind of reaction where A becomes products. How can we find the concentration of the reactants as a function of time, and sometimes it will also be as a function of the initial concentration. We want to find this specific dependence, and to find this solution it will involve some calculus, but something that we will split the problem is that it will depend on the order. In other words, it will depend on the exponent on the rate law. You'll see a different function depending on if the order is 0, 1, or 2. In this video we're going to solve when you have first order. It should make sense that depending on the order, the dependence of the concentration versus time will be different. The higher the exponent, the higher the rate will be in which the reactants disappear. So bear with me, we will have to solve a differential equation in which the definition of the rate is how much the concentration of reactants changes with time, and we, by definition of the rate law, we said that this is first order, so it's going to be the kinetic constant times the concentration. What we're going to do first is to move everything that depends on A to this side and everything that depends on T to this side. So what you have here is that we have moved the concentration to this side, and you have a differential of A and differential of T. You add it up, so in other words you do the integral, so you have an integral of 1 over x. Hopefully you know that it's a logarithm of x between whatever x0 and x, right? So between x0 and x, right? So but in this case you will have the logarithm of A between what limits? Between the initial concentration and the other side of the limit will be concentration at any given time. That is the logarithm of A minus the logarithm of A0, the initial concentration. On this side of the integral, it's trivial. It'll be T minus 0, or in other words, T, well in this case, sorry, the KT. Alright, notice that we move the negative to this side, so let me then do it well. If the negative is on this side, this will be negative KT. Alright, you will definitely have available these equations in your formula sheet. However, you should know where they come from. It should not look like magic. At the same time, notice that this is the logarithmic form of our solution. This is the same that we have here. You will see also that you can express this in exponential form. If you take exponents on both sides, you will see that this is the typical exponential decay that you have seen before. Okay? Or if you will, in a different form, you move the initial concentration to the other side. This is the well-known exponential decay. In other words, every time you see an exponential decay, you can identify that as a first-order kinetics. There's another concept called the half-life. The half-life is very useful also in radioactivity. We will, of course, study radioactivity as well from the kinetics point of view. But the imposition that you put in is that at what time the concentration has been halved with respect to the initial concentration. So you just need to plug this in here and solve for T. What you find is that the half-life for first order reaction does not depend on the initial concentration. It's just logarithm of 2 divided by K. You should be able to find this, okay? You should be able to manipulate from one equation to another, and again, the remarkable thing is that does not depend on the initial concentration. Okay? The time that it takes for a concentration to be halved does not depend on how much that initial concentration is, as long as you have a first order kinetics. Now, how can we use this experimentally? Notice that in here, one form of this equation is the logarithm of the concentration. If you plot the logarithm versus time, what you will see is that this is your y, the time is your x, negative k is your slope, and logarithm of the initial concentration is your y-intercept. So we will use this technique to experimentally find kinetic constants, and also, if you will, the initial concentration, even though initial concentration is something we know. So, for example, let me give you an example. Experimentally, how would you go about measuring the rate constant, for example? You set up a kinetics in which at a different points in time for the reaction, the decomposition of dinitrogen pentoxide, you measure the concentration. So in a spreadsheet, you may want to do the logarithm of that concentration and you plot. This will be your y-axis, this will be your x-axis, and if it gives a straight line, it means that it's a first order reaction. And if that straight line gives you this equation, you can identify the slope as 0.035 minutes to the minus 1. Notice that for first order, the units of the kinetic constant is the inverse of time, and if we are measuring time as minutes, the units of the kinetic constant will be minutes to the minus 1, and the y-intercept is 4.1. Okay, well, in other words, the initial concentration will be negative to 4.1 molar. All right, so we have seen, therefore, how we can use the result of solving the differential equation to actually calculate the kinetic constant, or if you will, even the initial concentration of reactants.